Hello everyone, my name is Samuel, and in this week's overview, I will be walking through three important algorithm topics: search trees, sorting and selection, and graphs. So these are all essential tools for organizing, processing, and connecting data. Let us start with search trees overview. So, search trees help us efficiently search, insert, and delete data. Binary search trees follow a left small, right large pattern, whereas balanced search trees like AVL and red black trees help maintain performance even as more data is added. For example, I practiced inserting values like 50, 30, and 70 into a binary search tree and learned how AVL rotations keep the tree balanced. A good example of search trees that I also did was solving exercises where I had to rebalance an AVL tree after inserting values like 10, 20, and 30, for instance, which needed a single rotation. I also worked with red black trees to maintain balance and color rules. These examples help me understand how trees adapt dynamically. Alright, let's jump into sorting algorithms. Sorting is really all about putting data in order, pretty self explanatory. And I learned merge sort, which uses divide and conquer, which is a method, to consistently get a time complexity of O(n) log of n performance. I also used quicksort on test lists like 3, 7, 8, 5, 2, 1, 9, 5, 4, etc. To practice partitioning and see how it performs differently depending on pivot choices. Another example that I used were merge sort applications with a list such as 38, 27, 48, 39, 82, and 10. All right. So, as far as comparing sorting approaches is concerned, merge sort always splits evenly. So, while quicksort depends on the pivot, I compared my quicksort results with Python's built and sorted to check accuracy. So this helped me enforce how different sorting strategies apply in real life scenarios like large file processing, for instance. So yeah, I ran a quick sort on a list of 378521954. And quick sort is often faster, but the worst case is the time complexity of O n squared. All right, let's dive into selection. So selection is about finding the k smallest element without sorting everything entirely. So you don't do any full form of sorting. And a great way of practicing problems solving the fourth smallest number, for instance, is what I did using quick select. It's useful when you just need to find the median or a threshold value quickly in a large data set. So yeah, selection is used in applications like finding medians or thresholds, um, which is essential for data analysis tasks most often. All right, graph overviews. Graph really help represent relationships. So I built graphs with nodes and edges to simulate networks and basic maps. Understanding how graphs model real world structures like social connections was truly a highlight for me. So, like I mentioned, it uses modal relationships using nodes, also known as vertices, and connections, which are also known as edges. Very useful for networks, maps, and recommendations. Can either be direct or undirected, weighted or unweighted. And yeah, some examples were building five nodes and six edges using an adjacency list, and visualized connections for basic recommendation system was something that I did to get a deeper understanding as well. For graph representation, I used both agency lists and matrices. So lists work better for sparse graphs, and matrices are more efficient for dense ones. Python implementation uses dictionaries and lists, which I used. So I built a Python version of both for a for node graph to see the trade offs in memory and speed. Both agency lists, adjacency lists, and adjacency matrices. And yeah, implemented both versions and then I compared their storages. For graph algorithms, what I did is I practiced both depth first. Oof, another tongue twister. Depth first and breadth first traversals to explore graphs. I also used Dijkstra's algorithm to find shortest paths between nodes, like from A to F, in weighted graphs. This showed how useful these algorithms are in geospatial systems and how it helps with routing problems as well. Actually, let me go back. So, minimum spanning tree connect everything with lowest cost. Just wanted to point that out there. All right, so for advanced graph users, advanced topics like union, find really helped me check for cycles and manage disjoint sets. So I solved MSC problems using Kruskal's algorithm and I did topological sorting for DAGs. These exercises really gave me a deeper understanding of graph complexities. Thank you very much for listening. This was the final week of this algorithms class and my overview for week 5. Hope you enjoyed it.